Good evening, everyone, and I hope I am audible. Yeah. Good evening, everyone. Welcome to the last live session for the course Design of Reinforced Concrete Structure offered by NPTL. I am Harshit Agrawal, a PMRF research scholar from IIT Bombay, and I will be taking weekly sessions throughout the end of this course. And today is the last session. Okay. So, what are these sessions all about? So, these are doubt clearing and interaction sessions. They were conducted weekly every Tuesday from 6 p.m. to 8 p.m. until the course runs. And in these session, we interacted by answering to the questions that I asked in the chat box, posting the queries in the chat box, or by raising and unmuting and asking your queries. Apart from the class or live session, you can always use the discussion forum of the course, and the questions or your queries there will be addressed through the discussion forum itself or in the next live session. How this interactive sessions will help you? It will help you to answer your graded assignments easily and will help you to further understand complex topics holistically. Okay, so just the outline of today's live session. We will first recap what we discussed in the last live session, that was for week 11 of the course, and then I will present you an overview, and then we will discuss the week 12 of the course, in which we will first discuss about various RC elements and the forces acting on them. Then we will have an overview of discussion that we have till the week 12, like from week 1 to week 11, what all we have learned in these sessions. I will try to summarize them in a brief manner and I will describe you that. Then we will see some design analogy for a RC building, like if you want to design an RC structure, a whole RC structure, and what all analogy you need to keep in your mind while designing. And then we will see a simple numerical on a multi-story RC building. Today we will see a office building, and I will guide you step by step, like how an office building, if you are asked to design, how generally the thinking behind it runs. Okay, and we will have some basic introduction to the seismic design force also, IS 1893. We will just have an overview of that also while we do the designing. Okay, and finally we will conclude the course and the session. So, in the last live session, that was for week 11 of the course, we talked about torsional movement. So, torsional is something like twisting movement that occurs on a junction. So, suppose I have a beam and a slab junction. So the moment that is acting in the slab can generate torsion in the beam and vice versa. So we talked about when such torsional moment also occurs in an RC element, how we deal with it. Okay. For this, we saw different kinds of RC, different components of RC and forces. So torsion is one of the four main force element that we design for, and it occurs at junctions of beams, columns, or beams and slabs, and all these combination where there is a joint. Okay, there is a chance of torsional moment to occur. In the slab design also, we talked in continuous slabs design with fixed support also, we talked about torsional reinforcement there also, so you can catch some reference from there also. Then we saw how torsional moment is taken into account. So it is not a different kind of reinforcement or something we provide. We just take into account torsion by defining equivalent shear and equivalent bending moment. So VU and MU we know, we calculate from the design load, and VT and MT is the additional moment and additional shear that are coming due to torsion. Okay, so we defined the equation how this torsion will be taken into account for both shear and bending. Okay, and apart from shear and bending, how it also affect the transverse reinforcement that we provide. And finally, we saw a design of RC beam that is under torsional moment. Okay, so the same lecture, the week 11 live session, has been uploaded on YouTube channel also. You can always go through the channel and revisit the question and the theory behind it. Okay. Now, just to summarize the whole course, design of reinforced concrete structure, the main purpose of the course was to see the interaction between the structural element and the structural forces. So, what are the different structural element we talked throughout the course? Those were slabs, beams, columns, staircase, and footing. So when we are talking about design point of view, we go from up to down. We first start with slabs, then we go to beams, then we go to columns, then we go to staircase, and then we go to design. But actually in construction it is the opposite way around. Okay, so the design and the construction are both opposite to each other, that we know. Now, among these structural element, the five major structural element, what are the forces for which we aim to design for? It is flexure, or we can say bending. There is shear, there is axial, and there is torsion. So we have seen flexure, how it contributes in all the elements. Shear, we saw shear contribution in beams and in slabs. We need to concern for shear. Axial, we talked mainly in columns, axial load that comes in a column, and how it can make like generate additional moment also when there is long column. And torsion, it can occur in the interaction of slabs beams or beams columns, that we introduced. Okay, now what we will do today we will just have a recap of all these structural elements with these forces, how we learned about designing from week from live session 2 to live session 11. Because in live session 1 we just had an introduction to the course where we didn't discuss about anything about design, but we discussed about working stress method and limit state method. So now we will just move on with the design part. Okay, so first we will start with the slab. So we know slab we design for flexure. Okay, and how what slab is, those whose thickness is less compared to length and breadth, and they are used to transverse load acting on a floor to beams and columns supporting by bending in one direction or other. So this is a technical definition of what is slab. Okay, now when we talk about design of slab, I've tried to summarize the whole design that we learned in a simple diagram point of view. So these discussion we had in live session 5 and 6, you can always revisit the discussion there. So first of all, the main thing is to calculate the effective length of the slab. And how we do that? By using the clause 22.2 of IS 456, we can get the effective span of the slab. Now the slab is spanning in two direction, x and y. So we know the ly and lx. Okay, effective span in both the direction. Based on the ratio of ly by lx, we classify slab in two categories. Okay, if my ly by lx is less than 2, it is one way slab, and if it is greater than 2, it is two-way slab. So for both, the design part is different. Okay, one way slab are those which span only along the shorter side. So we need to provide reinforcement along the opposite direction, only along one pair of opposite sides. Okay, and for this, initially we have the L by D ratio we choose. We provide the main reinforcement, we decide the spacing, and we provide the distribution reinforcement along the opposite direction, and we do the deflection check. So this all thing we introduced in the week live session 5. Okay. Now, when we talk about two-way slabs, these slabs are those which can span along both the direction, and thus supports are needed along all the four sides. So in this, we first saw how load distribution is done. So here load distribution is simple, half on one side and half on other side. But when my slab is spanning along both the direction, my load distribution diagram appears like this. Okay, and for this load distribution diagram we saw different cases also, my edge is continuous or not continuous, and how I take factor of alpha x, alpha y, beta x, and beta y based on the dimension of the slab. And based on that, we saw how we can calculate the bending moment across both the direction, positive and negative both, and how we provide the main reinforcement, spacing, and if my ends are restrained, how we provide the torsional reinforcement, finally do a deflection check. So this was the whole overview of slab design, how we did the design of RC slab. Okay, now from slab we move to beams. So beams are the supporting elements of the slab, and how we design for them. So the design part we learned in live session 2 and 3. So the first case is to determine the limiting moment of resistance. Suppose I know the dimension of my beam. Okay, and I know the grade of the concrete and the grade of the steel I am using. So as per annexure G of IS 456, I can just keep that also in loop. So as per annexure G of IS 456, you can see in the on this point C how we calculate the limiting moment of resistance. Okay, XU max by D you can obtain like from the clause 38.1, in which it is given for different grade of steel how XU max by D value will change, and basically you can get the MU limiting value. Once we get the MU limiting value, based on the moment that is acting on our section, we can decide whether it is a singly reinforced beam or a doubly reinforced section. So if my ultimate moment that is acting on the beam is more than limiting moment, then we need to go for a doubly reinforced section, doubly reinforced beam. Or if it is less than the mu limiting, then we go for a singly reinforced beam. So for that we saw how stress strain distribution is done. We saw different assumptions that we take into account, like maximum stress strain in concrete is taken as 0.0035, and what is the maximum strain that the steel can take. We saw how the stress block will appear, how we equate the forces and the movement that it is generating, how we calculate the lever arm distance, and finally how we decide how much reinforcement we need to provide. So this all thing we can again, you can always revisit an XZG of IS 456 to have a look of how all the relationships that is taken into account while designing. So here you calculate XU by D, then knowing MU you can calculate AST. Okay, and with AST you can calculate the number of bars and the spacing you need to provide, and if it is fitting in your section design or not, or you need to redesign. Okay, and in cases where your mu is greater than mu limiting, we saw doubly reinforced beam design, where we first design for a singly reinforced beam under balanced condition, and then for extra moment we provide reinforcement in the compression side also. So for that also in live session 3 we saw how this designing is done, and we saw numerical on it. Okay. Now this was all the cases when the beam is in flexure, beam and slabs in flexure. When there is moment, how we provide reinforcement, the main reinforcement to counter the moment, bending moment acting on the slabs or beams. Okay. One more case. Okay, when we talk about RC beam, there can be flange section also. So slabs and beams generally on site, they are not designed separately, but they are taken as a single member, which is known as flange section. Okay, so you can see a L beam that can occur at the external section, or in the middle internal section you can see a T beam kind of thing, which is formed by interaction of beam and slab. So in these cases also we saw three different cases based on the depth of the neutral axis and how we design for it. Okay, so in NHZ G2 of IS 456, again you can find this all relationships of design, and the same we also discussed in live session 3 also. So here in G2 you can see all the design cases and all the formulas relationships that will relate to this design have been mentioned. The same we also discussed in the live session 3, so you can always revisit that session again to have an recap of the thing. Okay, so till now whatever we discussed was for the design of flexure in beams and slab, but shear can also be a problem for which we need to take into account. So when we talk about beam, we saw how shear failure can occur, and we also saw how shear comes into action. Okay, so for resisting the shear we provide stirrups. So there are three ways to provide stirrup: either in the form of closed loop, which is known as single legged, two-legged, four-legged or six-legged stirrup, or we can provide bend up bars, or we can provide inclined stirrup. But generally this is the most preferred way for resisting the shear forces. And we saw three conditions, like if my shear force that is acting, it is more than tau c max, then we need to redesign the structure. If it is less than tau c max by more than the shear resistance that concrete can offer, we provide shear reinforcement, and if it is less than both, then we provide nominal reinforcement. So you can always revisit the clause of like clause 26 I guess of IS 456, where the design of shear reinforcement is discussed, and table 19 and table 20 to calculate tau c and tau c max. Okay, the same thing we also discussed in live session 4. So the whole discussion of shear was done there, so you can always recap the session for having a go at it again. Okay, now from beams and slabs we move to RC columns. So columns are generally vertical compression members that carries compressive load, and their effective length is greater than three times the least lateral dimension. Okay. Now when we talk about column design, first point is to calculate the effective length. So how we calculate the effective length? Using table 28 of IS 456, which takes into account the restraint conditions on. Now, knowing the effective length, if my L effective by D is less than 12, we say it is a short column. So for short column, we saw three cases: axially loaded, uniaxially loaded, and biaxial loaded column, and we saw how design is done. So for axially loaded, we used clause 39.3 of IS 456 for design, and for uniaxial and biaxially loaded column, we used SP16. Okay, SP16, like moment force interaction charts we used, and we saw how design is done. Okay, clause 39 points is specifically for biaxially loaded column. We saw how the design is done. So in this, we first determine for short column. We first decide the dimension, then we provide the main reinforcement, and we talk about the transverse reinforcement. Okay. And if my L effective by D ratio is greater than 12, it is known as slender column. So it's slender column. My axial load also can generate some additional moment. So we first saw how this additional moment is calculated due to eccentricity, and then we saw how SP16 moment force interaction diagram can be used with clause 39.6 to design a slender column. So these all discussion we did in live session 7, 8, and 9, how the design part is carried out. Okay. And after this we talked about design of RC footings. Okay, so footings will take my bending. Okay, flexure. So we saw what is the need of footing. So role of footing is to supply the substructure load to the below structure part. Okay, so since soil is much weaker compared to concrete and steel, we need a higher area and volume of soil which is required to carry the given load, and thus we footing act as a load transfer element from a structure to its underlying soil. So we saw initially how we take into account the area of footing, how we decide the area of footing based on the interaction of two engineering domains. One is the structural engineering and one is the geotechnical engineering. So from geotechnical engineering, we get the safe bearing capacity and the properties of soil. And from structural engineering, we get the service load that is acting on the footing. And basically from interaction of both, we give us the area of footing that is required. Once we know the area of footing, we can determine what is the moment that is acting on the footing. Okay, on both the extremes, and based on those moment, once we got the dimension, the lateral dimension, we determine the thickness. For thickness, we have three conditions: it should resist bending moment without the need of compression force, and it should resist shear forces without the need of any shear reinforcement. So we saw where failure can occur due to bending, one way shear failure, and punching shear failure. And for based on all these three conditions, we can determine the thickness of our footing that we need. And knowing the bending moment that is acting, we can provide the main reinforcement along both the direction. So the same discussion we had in the live session 9. So there we saw in deep about all these conditions, how they came up, and the formulas that are used behind the designing, and finally we also solved a numerical on it. And after this, the final part that we discussed was design of an RC staircase. So staircase can be of different types. So staircase, the main purpose of staircase is to connect adjacent floors. Now they can be mainly classified into three types: doglet staircase. So these are like this. Where's my cursor? Okay. So these are dogleg staircase. These are staircase, and there can be circular staircase also. Mainly, we talked about design of straight staircase, in which we saw different dimension or different terminology related to staircase and how they pave their way in the designing part, how what are their general guidelines for designing. And we saw how the design of staircase is done. So first we calculate the effective span based on the distance between the supporting beam. We choose a trial depth of the underneath slab. So in the straight staircase there is a slab, supporting slab in between. Okay, so this slab is generally a one-way slab, we can say. So just the way we designed a slab, we again design a slab here. So we note the load acting on the slab. Okay, so we choose a trial depth of the unready slab, we do the load calculation from above, in which apart from the live load, we also calculate the dead load due to staircase steps also. Then we calculate the design moment. We provide the tensile reinforcement. We check for reinforcement depth if they are sufficient or not, and we provide the distribution seal. The same way we do in the one-way slab. Okay, so and this all discussion we had in live session 10, and we also saw numerical there for design. Okay, so this was all about from week 2 to week 10, whatever we discussed. In week 11, we talked about torsion that we just recapped during the start of the class. So that is something I am not covering again now. So any doubts in the discussion till now from week 2 to week 10? Any like major point that you have doubt about? Okay, if not, we will continue it. Okay, so this was a kind of summary of whatever we discussed from week 2 to week 10. Now, how to club them all together in design of a RC structure. Okay, so before going to that, we need to understand some basic considerations that we take when we are designing a multi-story RC building. So, RC building can be majorly classified into three domains: residential building, administrative or office building, and educational building. Generally, if you will see in design cases, dimensions like these are mentioned: 8 feet cross 10 feet, or 10 feet cross 10 feet, or something like that. Now we understood everything in terms of meters, so since these value are like in decimal places, that's why we talk about that's why it is mentioned in 8 feet in feet uh, designation, so that it is easy to understand. Okay, so for every kind of rooms or locations in a building, a standard size has been defined, or you can define a standard size. Like bedroom, it is generally 3 cross 3.6 meter, or 3 cross 4.2 meter, or 3.6 cross 4.2 meter. So in this way, you need to first design, or you need to plan. So if it is a office hall, what will be the dimension? If it is a cabin, what will be the dimension? If it is a restroom, what will be the dimension? If it is a cooking area, what will be the dimension? You need to fix before you are moving into the design. Okay, now once you are clear with the type of building and the type of dimensions you need to provide, you need to we need to proceed with the design, beam spacings and slab thickness. Okay, so I have slabs. Okay, your dimension should be such that the spacing between the beams is adequate. Your columns are generally provided, we know, at the junction, so you should know where the columns needs to be provided at all the beam, at all the junctions. Okay, at the interaction of two slabs, or where two beams from opposite direction are interacting, there is one column. So this is how we like should have a general knowledge of how a design can be carried out. Okay, where we need to provide a beam, where need to provide a column, what should be the dimension of everything, and like that. Okay, now we'll try to implement these things in a question now. Okay, so what is the problem? I won't be doing all the numerical calculation and everything, but I will just provide you a basic guideline. Like when we talk about a building, a RC building, how thinking is developed behind designing that building. So how we first decide what are the requirements, then how we prepare the skeleton, how we collect the basic data from the the in charge, who is in charge of the project. Then based on those basic data, how we assume some data like dimensions of my beams, columns, slab, everything, how I make initial assumptions of my things. Then how I calculate the load. The load is the major part, because there are different kinds of load: dead load, live load, earthquake load. How we take into account all those things. When I'm talking about earthquake load, how I calculate the load, and then how I calculate the moment acting along all the different on different elements, and how I design finally. The design part we have learned, the slab, beams, column, that we know, but how we reach till that stage, that we need to understand. Okay, so we'll see a basic understanding of how a G+3 story office building can be designed if it is located in a seismic zone 3 area. Okay, so the first step of designing an RC building is to define the requirements. Okay, so this is an arbitrary question. So we say, suppose I have number of floors that require are 3. Okay, and on each floor I need can 10 cabins. Okay, okay. Suppose this is the demand. At each floor there should be 10 cabins. There should be 3 floors. Okay. Uh, Number of restrooms at each floor. Again, it is mentioned. Suppose there are 2. Okay. Number of discussion areas, when we are talking about the office building, discussion area can also come into account. So number of discussion areas or areas where there are cubicles. Okay, so suppose that is again 2 on each floor. And I will have a staircase area, that is like obvious. And I have a walkway area or balcony or something, you can say. Okay, so these are basic requirements of a office building. Suppose I am having this basic requirement of an office building. Now, based on this basic requirement, I will first develop a base skeleton. Okay, so how will my base skeleton appear? Okay, so suppose this is my top view of the building. Okay, here in between I have a staircase area. Okay, and this side I have half number of cabins, everything divided in half, so each floor requirement will be divided half and half on both the side. Okay, so suppose here uh, this part. Okay, this is my staircase. Let us assume this is the staircase, not staircase, sorry, it is the walkway area. Okay, staircase is in between, no? So this is my walkway area, and this part above is my office area. So in that also I need a common area, or the area discussion room or the cubicle area. So suppose this is my that cubicle area. Okay, and on the sides I will have my office and the restroom. So suppose I need what 5 office, 10 office on each floor. So suppose these are my office: 1, 2, 3, 4, 5, and this is my common room or washroom area. Okay, and similarly here also: 1, 2, 3, 4, 5 office area, and 1 washroom area. So suppose this is my basic skeleton, the top view of a floor. Okay, I can decide the dimension. Okay, suppose I am fixing a dimension of 5 meter along this side and 2.5 meter along this side. Okay, same here, same here, same here. Okay, this area in between, suppose it is, so this is 5 meter. Okay, this again I am fixing 5 meter, and similarly on the opposite side also, and here also again 5 meter, 5 meter, 5 meter. Okay, 3 5 meter office dimension, and this is 2.5 meter. So in this way, if we decide the dimension of all the offices and of all area, we can have a total dimension of my floor that can be easily defined upon based on the area availability and the demand and the requirement of the area of a particular office or a discussion room. Okay, so this is the second step with preparing a base skeleton by discussing with the concerned party. Okay, now this is the top view. What is the dimension of the elevation? How along elevation, how it is uh, demanding. Okay, so that sketch was done. Now when I am talking about elevation view, like front view, so it will be like a frame structure. Just wait a minute. Okay, so it will be like a frame structure. Okay, the columns will be decided based on the lateral dimension that we provide, and there will be three floors. Okay, the spacing in between spacing, it will be 5 meter, 5 meter, 5 meter, I guess. Okay, based on what we decided earlier. Okay, and the height of each floor, suppose it is also 5 meter. Okay, so from the top view we had the lateral dimension all fixed, and from the front view you have the vertical dimension. Okay, so in this way we have the complete knowledge of how my office building will appear. Okay, now when I'm clear with the dimension part and everything, and the skeleton, the base skeleton part, the next step is to collect the basic data. From basic data I mean the grade of the concrete, the grade of the steel, the dimensions, everything. Okay, so how we decide upon that? Okay, so when I'm talking about basic data, I need to have an information about concrete grade. Okay, whether it's M20, M35, M25, M30, whatever I'm using. Steel grade, what steel grade it will be used, Fe 250 or Fe 415 or Fe 500. Okay, after this, in basic data, brick wall thickness can also come. Okay, so brick wall thickness, what we need to provide, suppose 125 mm I am providing internally and 250 mm I can provide external, whatever we need to provide. Staircase, so what will be the width of the staircase that we need to provide, that can also come in the basic data. So staircase width, it can go from 1000 mm to like 1250 mm, whatever width we need to design for staircase. Apart from this, what all can come in basic data? Earthquake zone. Okay, what, in which zone it belongs? So earthquake zone, that was post 3 or zone 3 it belongs. Live load, so we can decide upon the live load on each floor. Corridor, the walkway area or the corridor we say. Staircase. Okay, so suppose on floor my live load is 3 kilonewton per meter square, and on corridors and staircase it is 4 kilonewton per meter square. Exact value you can always use IS 875 to get the exact value of how which load we need to consider while design. And there can be roof. On roof we again say suppose it is 3 kilonewton per meter square. So these are again some basic data, the geotechnical information of the subsoil. Okay, so in which what all things will come, the safe bearing capacity of soil. Okay, the geotechnical department provide you the safe bearing capacity of soil, and the depth of foundation that we need to go for. Okay, okay, this information again will come into some of the basic data. So these are different kinds of basic data that we need to collect before we move into the designing part. So what all we saw, first we talked the defining the requirements, what is the requirement from the building. Then we prepared a base skeleton where we saw what all dimensions we need to go for, lateral dimensions also, distribution also, and vertical dimension also. Then we collected the basic information regarding the materials that will be used. Okay, now after having the basic information, the next part is to have the assumed data. Now basic data we know, certain things we need to assume. So what all things will come in my assumed data? So things like thickness or dimensions. Okay, so thickness of slab will be my assumed data. Okay, floor finish, what is the thickness of floor finish will be again something I need to assume before designing. Thickness of ceiling and plaster, Again, it will be an assumed data. Unit weight of concrete that we generally take as 25 kilonewton per meter cube. Of floor finish that we take as 24 kilonewton per meter cube. Plastering again we take as 24 kilonewton per meter cube. So these are some as data that you need to assume and need to collect. Okay, after that, dimensions. So in dimensions we talk about columns. Okay, what are the dimension of column, internal, external, if they are different, so what are the dimension that we will initially assume. Beams, again we'll assume a dimension, suppose 300 cross 500 I'm providing. And slab thickness, what is the thickness of the slab that I need to go with, suppose I'm providing 100 thick slab or 125 thick slab, whatever I need to provide. So these are some of the data that we need to assume. Okay, now once we know the basic data and the some of the assumed data, we can go with the next step, that is calculation of dead load and live load. So how this is done. Okay, since we had a detailed discussion in the one of the question that was discussed in week 12, I'm just providing you an overview. Okay, so once you know all the basic information about design, we can go with the calculation of load. So simply, if I'm assuming I'm providing 125 thick slab, so my dead weight of the slab will be nothing but 0.125 times 25. Okay, so it will be 1.3.125 kilonewton per meter cube. So this will be my dead load of slab. Similarly for floor finish, also suppose 30 thick floor finish we are providing, so we can calculate zero point zero 0.03 into 24, so 0.720 will be my dead load of floor finish. Similarly for ceiling plaster, suppose 6 thick ceiling plaster we are providing, so again we can calculate the dead load for that. 0.006 into 24, it will come out to be 0.114 kilonewton per meter cube. And then dead load of slab, floor finish and ceiling plaster together, what it will be. Okay, so when we are designing what is the imposed load on a beam, so we need all three in combination. So finish load plus slab we can add and calculate, and we finally can calculate the dead load of brick wall. Okay, so we know the unit weight, suppose it is 25 kilonewton per meter cube only, or 20 kilonewton per meter cube. We know the thickness. Okay, 0.125 or 250 or 125 and we know the height. Okay, height of the brick wall, so we can calculate the dead load of the brick wall also. So suppose it is like 20 is the unit weight, suppose the thickness is 250 so 0.25, and suppose the height, effective height, so you need to subtract the depth of the beam first. Okay, so when you are talking about like height of the brick wall, so these are two floors. Okay, in between floor I have a distance of 5 meter, but my depth of the beam is 500 so this part is my beam, so this is my brick wall effective. Okay, so my dimension of brick wall, it will come out to be 5 minus zero point 0.5. So such, considering such things, you can calculate the dead weight of the brick wall also. Once this load calculation is done, what you can do, you can calculate what is the net load acting on a beam or a slab, on a beam basically. So you know different kinds of load, that is dead load of different elements, so that you can add. So like over a beam. Okay, so if I say, if this is a beam, on the beam the weight will be due to slab. Okay, the brick wall and the finishes. So if you know the dead weight of each component separately, you can calculate the UDL acting on the beam. Okay, you know the dimension of the beam, so you can calculate what is the UDL load acting on the beam. So same calculation you can do for all the elements. Okay, all the beams. If my thickness of wall is changing from internal to external, then for external beam the load acting will be different. For internal beam the load acting will be different. So in this way, once we know all the load calculation, all the dead load, we can go with the determining the UDL on a beam. And once this is done, we can determine the total load acting on a floor. Okay. So total load. This was for dead load. Similarly, for live load also you can calculate the total live load acting on the floor, and the total load acting on the floor will be nothing but dead load plus live load. So for each floor, this load calculation can be done. Okay. Now, once we have done the calculation of dead load and live load, the next step is the calculation of earthquake load. And for this, we refer to IS 1893. Okay. So as per IS 1893, what we need to know. So just a second. Okay, now I know the zone. Okay, I will show you the code here. So this is IS 1893. We won't discuss it into depth because it is a separate topic of discussion that you will have as a different course. Okay, so in this code, the whole country is divided into different zones. So based on the location of your structure, you are categorized in a particular zone. So we are talking about zone 3. So you can see where zone 3 lies. Okay, the area where zone 3 belongs. So suppose I am talking about a structure in zone 3. So there are different parameters that we need to define for an earthquake, for a seismic zone. So here in the code you will get the basic in like parameters and the definition of all those parameters. So I will go directly on to the main charts that help us to design the calculate the shear that is acting due to earthquake activities. So this is the first parameter, that is a horizontal acceleration. So based on the location of your structure, we get different values of different parameters, like Z, I, SA by G, everything. So you can see here, based on the type of soil, you can calculate the SA by G value. Based on the zone, seismic zone you are present in, you get the zone factor value. And based on all the things, you get the horizontal acceleration that may be acting on the structure if seismic activity arises in the zone. And once you know the horizontal acceleration which can occur in the structure, you calculate the base shear. So AH you calculate based on the zone in which you belong. The net load of the building, the net weight of the building, we know, as we calculated the dead load and live load for each floor, summing for all the floors, we will get the net load that will be acting on the floor level of the building. And based on multiplying both the things, we calculate the base shear, or what is the shear that will be generated when seismic activity arises in that zone. Okay, now this base shear, so suppose this is my frame structure of the building. Okay, and suppose earthquake activity occurs in the building, so I know the base shear. Okay, now this base shear will be distributed along each floor. So how that distribution is done, that is again given in the IS 456. So some part of the shear will go on to the first floor, some part of the shear will come to second floor, some part of the shear will come to third floor, and so remaining part will go to the top floor. So addition of all these forces will be your base shear. And as per IS 1893, you can calculate how this shear is distributed. Okay, so this is the formula. Okay, the design base shear for each floor, how that is distributing along the height, depends upon the weight of each floor and the height of the floor. Okay, so this is how this division is done. Now we know the effect of earthquake load. Okay, this is the earthquake load component that is coming, and dead load and live load we calculated using the basic design parameters. Now we know all the different kinds of loads that are acting on a building. So once we know this, we can go for the design part. Okay, now in case of design, we learned how we proceed in design from slabs, then beams and columns, then footing, and then staircase, and then footing. So once we know all the load acting, we can design for a slab. So suppose this is my slab of a particular floor. Okay, I know the UDL. Okay, I calculated the UDL, what is acting on that floor. Okay, and I know the dimension of my slab. Initially, I have fixed the dimension of my floors. I know the dimension of the slab. In our case, I suppose it was 5 meter cross 2.5 meters. So since the ratio is 2, it is a two-way slab. Okay, and we know the UDL that is acting, so we can appropriately design for the two-way slab. Again, in two-way slab, we can classify if my slab is internal based on the restrainment or based on the continuity of the edges. We can determine from the 9 cases which kind of slab is this, and we can choose the parameter alpha x, alpha y, beta x, beta y. Okay, and based on that we can calculate the moment. Once we calculate the moment, we can design the slab for different conditions. Like internal slab we need to design separately, external slab we will design separately. Okay, this part was in slab. Okay, so this is how the slab design is done. Once you have designed the slab, you need to design the beams and columns. So for that, you first need to carry out the frame analysis. So this might be covered in some different course. I will just provide you an overview. So if I see from a side view, my building will appear like a frame. Okay. So the horizontal portions are my beams and the vertical portions are my column. I know the UDL acting on all the floors in and along all the elements. Okay, so I know like UDL here what is the uniformly distributed load occurring, and I know the horizontal force also that I got from seismic activity. Okay, now based on this we can calculate the moment and the shear that each column and beam will experience. So simple frame analysis, it can be carried out. We know the dimension, lateral, horizontal dimension, vertical dimensions, and using standard codes and practices, you can calculate the bending moment and the shear force generating across each joint. Okay. Now, once we know the bending moment and the shear force, we can design for the beams and the columns. Okay. So, simple beams. Okay, you know the moment. Sorry. Okay, a beam is there. You know what moment is acting on the beam and what is the uniformly distributed load on the beam. Okay, you can calculate how much reinforcement it should be provided, and similarly for column, you know the axial load acting on the column and the moment that has been generated on the column, so you can design for the column also. You know, we also know the dimension, 5 meters the length. Lateral dimension also we can fix initially, like 300 cross to 500 lateral dimension, or a square column or a circular column, any kind of column that we fix, we once we know the moment and the axial load that is acting, we can design the beams and the columns. So in this way all the design of beams and the columns are carried out, and finally when all the superstructure design has been done, including staircase, so initially we fix the width of the staircase also, so the design of staircase can also be carried out. Since we know the height of two floors, the distance between two floors, the staircase also can be designed. Once you have designed all the superstructure part, we can go for the design of foundation. Since in foundation we need to calculate the total dead load and the imposed load. Okay, so dead load we know, imposed load also we can calculate, so we know the total load. Based on the total load we can design for, like if we need a combined footing or a isolated footing or a mat footing or a raft footing or a pile foundation, whatever kind of foundation or footing we need, we can design for it. We know the data from the geotechnical section also, what is the safe bearing capacity of the soil, if it is varying with depth or not, everything information we have, so we can design the foundation. Okay, so this is generally how a design of a G+3 story building will be carried out. Any doubts in this? I provided a brief overview because the detailed discussion was done in the live session, and carrying out a whole new problem would take a lot of time. So that this was just in general overview of how we apply the design of various elements that we have seen. The major part is the initial calculation of load and moment. How that is done, that I tried to explain in a simpler way. Any doubts in the discussion? Okay, so
No, sir.
if there are no doubts, this was all about the course. Okay, so in this course, we first started with the discussion about basic design, like working stress method of design, limit state method of design, ultimate load method of design. That is first that we talked about. Then we moved into design of various elements of a RC building, where we first saw the design of beam, singly reinforced, doubly reinforced in flexure and in shear, if shear comes into account, how we design for stirrups. Then we moved to slabs, in which we saw design of one-way slab and two-way slab, and all the restrainment and confinement, how we considered them. After we moved into columns, short column, slender column, how they are designed. Then we moved into design of footings, in which we mainly saw an isolated footing design, and staircase, in which we saw the design of a straight staircase, and how finally torsion is taken into account. So this was all from week 1 to week 11. In today's class, we talk about general considerations that is taken when an RC multi-story building is designed, and then we understood step by step how a G+3 story office building design could be carried out, how the thinking behind it is generated. Okay, so with this, we conclude the course design of reinforced concrete structure. Any doubts in the discussion or general doubt in the course? Okay, so if there are no doubts, we will conclude the session. So I'm just attaching the link of the YouTube channels that you can refer again to have the go through the discussion of any of the particular section earlier. Okay, so with this, I will close the session. Thank you.
Sir, I have one doubt, sir.
You are not audible. Can you write in the chat box? There's some problem with the audio.
Okay, sir.
Just type in the chat box.
Hello.
So corners that are held down and corners that are not held down. So as we discussed in the week 6 or week 7, if I remember, so based on the restrainments that is there at the end, we determine whether the corners are held down or not held down. So generally, when we talk about certain elements where there can be negative and positive moments both. So we talked that the corners can experience some torsional activity and they can be held down. So that's why we design for torsion also in those cases. And when there is no negative moment that can generate at the corners, we generally say it is not held down. Uh, More into it, you can just refer to the week 6 content again. Like you will have a better clarity there also. Like generally all the internal sections, they are held down sections only. That I'm saying na, the slabs, the internal slabs, okay, where there's force acting from the top at the corners also, so those are held down, those are not freely available for bending. Some restraint are there at the top of those slabs. Mostly all the slabs that we are talking about, if it is a two-way slab, they are generally corners which are held down. On roof, the slabs that will be there, they can be considered as the corners which are not held down. Any other doubt? Yeah, thank you.
Sir, on examination, how much
Just
proportion of
type in
the
the chat
are
box. There's some problem with my audio. I'm not able to hear. Uh, where you're talking about questions? Like in the NPTEL exam or in general? Okay, so you have done the assignments that is weekly posted, na? So similar kind of questions will be asked. Like they will give you some conditions, like these are the condition how we will design a beam, or what is the reinforcement area we need to provide if such a moment is acting on a beam, or what is the stirrups that we need to design for, like that, or in a column. That all details I don't know, like how many questions and everything. But mostly it will be numerical only. You can always look into the previous year papers, like what all was asked. Like you can't remember all the clause, all the values, so they should allow the you to carry the code. Yeah, yeah. It should be allowed. Or if it is not allowed, all the codes or the clauses that are relevant to the question, they will be there attached. Like suppose, I'm just giving an example. Suppose I need to refer to this table, okay, for calculating the effective length. Okay, so table 28 would be there in the question paper, or these charts that we need to calculate for effective length, or when we need to calculate the coefficient of bending moment in case of two-way slabs. So both of these tables would be mentioned if code is not allowed to carry. Okay, the clauses will be mentioned to you. Basic formula you need to remember, like in case of beam, bending moment, what is the formula, how mu is related to xu by d, how from mu how we calculate ast, those basic formulas that you need to remember. But if there is something related to a value, it will be given. That I don't know about last year. Okay, so like just try to summarize everything, every element like this. Like how we talk na? In flexure, if I want to design a beam, I need to determine limiting moment. How it is determined, I need to remember the value. I need to remember the formula. Once I know the limiting moment, the moment acting on the beam, it would be given in the question, or you can calculate from the load. Okay, once you calculate, you know whether it is singly reinforced or doubly. If it is singly, you know the relationships, how you can obtain AST. If it is doubly, you know how it is designed. So just refer to this slide later on. It will help you to summarize all the things. Like in these 4 or 5 slides, you will be able to get the summary of the whole course. Okay, it will help you to prepare better. That you need to look here. I don't know whether they are available or not. But just refer to the assignment from week 1 to week 11. If you are able to, if you have gone through all the assignments, then the exam won't be an issue. If there are no further doubts, then we will end the session. Okay. Thank you and all the best.
Sir, wait, sir. I have one doubt, sir.